was there, because of which I was able to propose this FDP event. Thank you so much.
No problem. It's a pleasure.
Yeah, I hope we
Uh,
can start it.
yeah, sure. Just let me start uh, sharing my screen if that is okay.
Yeah, yeah, please. With your permission, I like to read your very brief profile. You please
Sure.
share the title slide and then I'll read the profile.
Okay. Just a minute. Just let.
Yes, please.
So you can see my screen now.
Yeah, it is coming. Yeah, yeah, it is there.
Okay. Okay.
It is there.
Yeah. Okay.
Yeah.
Yeah. Just let me know when you
So
want me to start.
definitely, definitely.
Sure.
So let me introduce Dr. Sumit to my speakers. Dr. Sumit Bhatia is a research staff member in AI Science Department at IBM Research AI New Delhi. Previously, he spent 3 years at IBM's Almadem Research Center, where he led the research efforts in Watson Knowledge Graph team. He holds a PhD from Penn State University, where he worked with the Sightseer group and developed novel algorithm and figure search capabilities for the Sightseer X digital library. His research interests are in information retrieval, text analytics, and natural language processing. We are really grateful that you are here, and I can see in your profile that you have worked with Watson Knowledge Graph at IBM. If my participants can recall, I introduced them to what is IBM Watson. So we will be delighted to listen something from you also regarding this. Thank you so much, sir, for being here. Over to you, sir.
Okay. Thank you. Thank you for the introduction. Okay. So I have planned my uh, session to be more practically oriented, use case oriented. So the way I have structured my slides is I'll give you a very brief introduction of what knowledge graphs are, and then instead of going into the plethora of tools and techniques that are used in knowledge graph constructions and their applications, which you will probably find in the papers, what I will do is I will give you a more hands-on and a more practical overview. So what I'll do is I'll just share my experience of working with the knowledge graph team at Watson, how we did it, and more importantly, I'll share some of the real use cases that we worked out. These use cases were motivated by different clients of IBM. IBM is an enterprise company. That means that IBM doesn't have a product or service for consumers like you and me. IBM offers products and solutions for different companies and government organizations. So a lot of problems that we work on at IBM, they are slightly, not slightly, but they are very different from the typical use cases you see in uh, companies like, let's say, Google, Facebook, or what you read about in newspapers and other media. So so the whole project when I was with the Watson team, we were working with some US government security agencies, and their use case was we want to use we want to help in some intelligence or security related applications, like how do we figure out if there are some criminals or some terrorists, and we get intelligence reports from all over the world, thousands of daily reports. So can we make use of these reports to find something more interesting and useful about the people we are trying to find. So that was the high level use case, and my team we actually started working very closely with them. And in the rest of the slides, I'll give you essentially my experience of working with the team, different problems we worked on, and how we solved some of the problems using knowledge graph. So that's how I've structured it. I thought it might be more interesting and more useful than just going into a survey of existing papers. So we'll start with this now, with this background, and in feel free to stop me in between if you have any questions. I would prefer it to be a more interactive session. So feel free to interrupt me and ask any questions that you may have. Okay, so let's start. So I generally start my lectures with this very simple question. Have you like used knowledge graphs before? That's a question I pose to my audience. So it's a question to you. Have you guys used knowledge graphs before? Maybe not, and I don't mean in terms of, let's say, your course projects or your research projects, but in general, have you made use of knowledge graphs in your, day-to-day life? Anyone? It's a question. Feel free to say either yes or no.
Sir, the participants are putting it in the chat.
Okay. Okay. I'm in full screen, so I'm not able to see it. Okay, got it.
Okay, I've seen that 2 to 3 have told yes
Okay.
and rest are
Okay.
saying no.
Okay. Sure. Thanks. Thanks for
Only
this.
10%. Only
Oh, okay.
10%.
Okay. Okay. So that's good to know, but unfortunately, most of you are incorrect. Actually, all of you have used knowledge graphs either one way or the other. It's just that you didn't know about it. And why I say so? Because if you have used Google, you have benefited from a knowledge graph, which is powering Google search. If you have shopped for anything on Amazon or Flipkart, then you have benefited from the knowledge graphs which these companies use. So Amazon and Flipkart, they have what they call as product graphs. If you have used Wikipedia, then also you have benefited from, and especially in case of Wikipedia, you probably have also contributed to Wikipedia's knowledge graph, which is the Wikidata, which is the knowledge graph equivalent of the information in Wikipedia and probably even more. And some of you who have ever played video games, there is a very good chance that video game was actually using knowledge graphs. So, and I actually came to know about this fact at a conference where I met an engineer from Electronic Arts. So it's a video game company, and he told me that they use knowledge graphs to represent stories and characters and their interactions within the video game. So all the things that a character does in a video game, that is tracked using a knowledge graph. So I think I I feel I'm confident to say that all of you have used knowledge graphs in one way or the other. It's just that most of the times they were hidden behind the scene. You were not knew that you are actually benefiting from a knowledge graph. Okay, so then the question may be, okay, so what exactly is a knowledge graph, right? So the funny thing here is that there is no clear single definition of what a knowledge graph is. Different people, different companies, different organizations, they build their own knowledge graphs to suit their requirements, and depending on their requirements, they have slightly different interpretations or different models for storing or creating their graphs. But in general, what we can all agree is that knowledge graphs are nothing, but they are just a structured representation of knowledge. And what do we mean by that? So essentially, when we say in terms of in a concrete definition, knowledge graphs are a structured representation of knowledge. And what is that? It's just a collection of facts about real world concepts. Okay. So, and these facts, they are represented as HRT. So each fact about some real world concept is converted into a triple. And a collection of these triples is your essentially your graph. right? Let me explain with the help of an example. Let us say there is a real world fact that a company called A9 is a subsidiary of Amazon. Okay, so here the things to notice that the words which are mentioned in red color, so they are entities. Entities are so real world entities, right? For example, persons, companies, countries, organizations. So all these are real world entities. So in a triple HRT triple, we call them as head and tail entities. So in this example, A9 is the head entity and Amazon is the tail entity. And the two entities in real world, they are connected by this relationship that A9 is the subsidiary organization of Amazon. So this is a real world fact, and we represent it as this that A9 is a subsidiary of Amazon. So to represent the fact, we need three things: two entities, two real world entities, and what is the connection between. So all the knowledge about the world can be encoded in terms of these triples. For example, Sumit is giving a lecture at NIT Kurukshetra. IBM has an office in New Delhi, right? So Arvind Kejriwal is Chief Minister of New Delhi. In all these examples, all these real life facts, you would have noticed there are two entities and they are connected by a relationship. So when entities are represented as nodes and relationships are presented as edges, essentially now you could see how a graph structure emerges, right? Example, let's say Sumit lives in Delhi, Delhi is in India, India is in Asia, right? So his whole path is coming into picture. And that's why we call it as knowledge graph. And all these facts are there. You could start from one entity and traverse the whole path. So that's the whole concept of knowledge graph, right? It's nothing fancy, nothing very complex. It's just this simple thing you need to remember. All the world knowledge or all the domain knowledge that you want to capture, you represent it as triples. Triples consist of entities and relationships. Entities become nodes, relationships become edges, and that allows you to move from one entity to another. That's everything you need to know about this concept of knowledge graph. So now you see, okay, so this is good. We have an understanding of knowledge graph, but then how do and I told that if you have used Google, then you probably use knowledge graph. So how does that help? So here is an example. So let's say you type this query into Google, say Steve Jobs' birthday, right? So typically, in your unstructured text or web pages, when the search works, it basically searches for web pages where Steve Jobs is mentioned and birthday is present, and then you do the ranking and present the results to the user. But when you have this structured information available in the form of triples, note that here Google figured out by using their graph that an entity called Steve Jobs is connected to another entity of type date 24 February 55 by this relationship date of birth, right? So Google could automatically figure this out by using your query that, oh, the user is looking for an entity called Steve Jobs and his birthday, which is captured by the relationship date of birth. So just by using the graph, Google could actually give you the top answer. It is so in absence of that, what would have happened? You would have taken to a website where Steve Jobs and birthday information would be present or maybe not be present. It could be Steve Jobs and his brother's birthday, something like that. Those issues could be there. But because of this graph, this information was present in a structured fashion. You could directly get an answer, right? So that's how knowledge graphs are used in search. That's one way. And the key message is that once you encode the information in a representation, it becomes easier for machines or computers to make sense of it and to make use of it. Okay, so let's consider one more example. Uh, so consider this portion of a knowledge graph. It contains some nodes. Let's say Steve Jobs, USA, Steve Ballmer, Bill Gates, Windows, Microsoft. So all these nodes are there. Edges show here that there is a connection between the two entities. Just for saving space on the figure and making it very less crowded, I have not mentioned the exact relationships, but let's just assume that there is a relationship between any entities that are connected by a red arrow. So from here we see that essentially you could actually see that if you see the entities that are connected to Steve Jobs, they are Apple, iPhone, Steve Wozniak, let's say, and likewise for Steve Ballmer, the entities are Seattle, Bill Gates. So you could see that these are the entities we actually know in the real world are connected to these persons. So once again, knowledge graph is but just a way to represent what we know about things in the real world. Their representation so computers can make use. Now here's one important observation. So let's say if someone asks you, is there a direct connection between, let's say, Steve Jobs and Steve Ballmer? By direct connection I mean, are they connected by a single relationship? Right? Obviously, there are indirect connections, in the sense that they are connected by the node USA. But if I ask someone that, is there a real connection between these two entities, a direct connection between these two entities, then yeah, what would be the answer? A lot of folks will say that no, there is no direct connection, right? And it seems very obvious. Uh, when it comes to knowledge graphs, that is not simply the case. We say that, you know, uh, we just say that we don't know if there is a relationship between Steve Jobs and Steve Ballmer. And this is essentially what is known as uh, open world assumption. And what does that mean is that if something which is not known to me, I don't say that it is false or it does not exist. I just say that, I don't know. So here, if someone asks a question, are Steve Jobs and Steve Ballmer brothers? Then I would say, I don't know. Because there is no fact in the graph that can tell me that either they are brothers or can tell me that they are not brothers. So I say that I don't know because the reason is that think about it this way. There is infinite amount of knowledge in this world, right? So you will never be able to have a knowledge graph which is complete, which has all the information, right? So in case of a question that is asked about something which is not in the graph, either you should have the information or you should have some information which clearly tells you that the question someone is asking is not possible. If that is not there, you just say that I don't know because today that fact is or information is not present in my graph, but maybe I'll have that information tomorrow. It's just that today I don't know, right? So this is an important assumption. Often this is overlooked, and sometimes it also might feel confusing. But this is an important assumption to always keep in mind while defining your or designing your applications, because you want to make sure that by error you don't claim something to be false, which could not be specified at that particular instant of time. So this is very important from a practical point of view. Okay, so now a few important points. So we talked about knowledge graph that there are entities and then there are nodes. But then can we say that every data set that is in form of a graph, can we call it a knowledge graph? Uh, I would say no. For example, let's say there is a citation network, which papers are citing which other papers, or the graph of the web, or road networks, right? Distance between points A and B, or the, let's say, map data, which is used by, let's say, Google Map, etc. So they are also represented as graphs. They have nodes, they have edges, but are they knowledge graphs? I would argue that they are not. So what is it that distinguishes a knowledge graph from some other graph data, right? So to answer that, let's just recall what exactly a knowledge graph is, right? So knowledge graph is is a representation of facts, and it consists of entities and their relationships. But there is another important concept behind knowledge graph, which we always remember. So there's this thing called a T box or a terminology box. So this terminology box essentially denotes the real world concepts and relationships between them. And in many cases, it is also known as the ontology or schema. So what do we mean by that? So essentially, the T box it basically specifies what type of entities will be stored in the graph and what type of relationships can occur between the entities in the graph. So think of T box as definition of your classes, and basically you are defining what are the different types of classes that could be in my graph. So for example, let's say I'm creating a knowledge graph for, let's say, academic domain, right? So my T box will say that, okay, in this word, entities will be of type, let's say, a professor, associate professor, assistant professor, undergraduate student, postgraduate student, research scholars, right? Universities, libraries, colleges. So these are the type of entities that will be present in my knowledge graph. So this is the definition. And then you'll also specify the types of relationships. So for example, you have relationships, let's say, supervisor or advisor of. So the T box will define that, there can be a relationship in the graph such that the head entity is always a professor and tail entity is always a student. So that you could have relationships like Professor X is supervisor of student Y. So here the T box is ensuring or it's defining that the supervisor relationship can only be between a professor and a research scholar. It cannot be a relationship between, let's say, an undergraduate student and professor, right? So undergraduate student cannot be a supervisor, PhD supervisor of professor. So the T box basically is defining what type of knowledge want to capture and what are the rules that define or you know create those knowledge. So that is your T box. And then you have what is known as an axiom box or an A box for short. A box is essentially the collection of actual facts such that these facts are in alignment with what the T box is defining. So in terms of the programming analogy, think of T box as the class definition and then A box is basically the instances of these classes, right? So to make it more clear, let us now consider an example. So let's say we have a T box that denotes three classes of entities, a person, a male, and a female. So it says that in our knowledge graph, all the nodes, they will either be of type person or male or female. And then the T box also defines certain types of relationships. So here we have relationships of type that a male, any entity of type male is also a person. Any entity of type female, a person. And any entity of type person is connected to another entity of type female by a relationship called as one. So in our knowledge graph, we'll have these three types of relationships and these three types of entities. So now let us try to see how the knowledge graphs will look like. So this is our T box. Now let us look at A box. So these are the facts that are added in our A box. So these are the facts such as, let's say, Rahul is a male, Sonia is a female, Priyanka is a female, right? So these are your basic facts. And then you also add a fact called Rahul has mother Sonia. So this relationship is a valid relationship because we can add this fact. Rahul is a male, we have already defined it, and Sonia is a female, we have already defined it, right? And this fact is then in accordance with what we have in our T box definition that a person can be connected with a has mother relationship to an entity of type female. So this is a correct fact. Then you can also add a fact like Priyanka has mother Sonia. Okay. So now here's a question. If someone adds this fact that Sonia has mother Rahul, then the knowledge graph should throw an error. And why it should throw an error? Because let us see the entities here. So the head entity Sonia, we know that it is a female and a female is a person. So this part of our relationship is satisfied. But the right part, which is the entity Rahul, Rahul is an entity of type male, right? But our T box says that, on the right hand side, I can only has an entity of type female when the relationship is husband. So then the knowledge graph says that, this is an error. It's an incorrect one because this is not in accordance with the definitions we have specified. So this is an important fact uh, for knowledge graphs, right? If you have defined your T box correctly, uh, you can ensure that a lot of information that is added to your graph will be correct and will be in accordance with the definitions of the T box. So you will not be, so the system will not allow you to have these type of incorrect informations, right? So this is what is called as consistency checking in knowledge bases. I'm sure the other lectures on semantic web and ontologies and other related topics will be covering these things. But that's one practical use case for that. Uh, any questions till this point?
I can see one question in the chat box, that is, can we include more than two entities in a box?
Yes, you can have multiple entities in a box, right? You see here we have all these different entities, Rahul, Sonia, Priyanka. So you can have multiple entities in the A box. Uh, I'm assuming the question is more about can a single relationship has more than two entities? So there are ways to do that, but in many cases, every relationship can be broken down into a form of the triples that we have defined, right? So essentially, let's say there the relationship is, let's say Sonia Gandhi has two children, Rahul Gandhi and Priyanka Gandhi, right? So you can actually decompose this into two individual facts, right? Sonia Gandhi has children, has child Rahul Gandhi. Sonia Gandhi has child Priyanka Gandhi, right? So most of the cases, you can actually specify any fact you want to specify into the form of the triples, where you have two entities and one relationship. There are ways of connecting, multiple entities in a single relationship, but internally they are also represented in this way, right? So it's just for the abstraction and simplification from the user end. Some systems might support these type of n-ary relationships, but ultimately those can also be decomposed into a set of these binary relationships.
There is a question from the participant. So one more very small answer question I would like to ask before proceeding further.
Mhm.
Kindly explain shortly that why are we going for all this when we were happy with our RDBMS? And Oracle is a company which is based on RDBMS, which is doing so fine, and we are also very happy with RDBMS. So why your A box and B box?
So RDBMS, so there is two things, right? Knowledge graph is not a database or a programming system. Knowledge graph is a conceptual thing, right? How do you want to encode the knowledge that you have? You can use any storage technology. RDBMS is a data storage technology, right? How do you store that data? So there are some knowledge graphs that are stored in relational databases. There are some knowledge graphs that are stored in graph databases, depending on what type of performance and what type of queries that will be there, right? So knowledge graph is not the comparison of knowledge graphs to RDBMS is not correct because they are not same things. Database management system is, as the name suggests, it's a system for storing and managing your data sets, like the schema and all that stuff. Knowledge graph is a conceptual subject, right? You can create a knowledge graph in an RDBMS database too. In fact, that's how many systems have built that. But then if there are some places where you want to do, let's say, some graph traversals, then in RDBMS world, the way to do that is by using lot of joins. And in graphs or data sets where you have millions of nodes, these joins become super heavy. So then people figured out that, RDBMS systems are not the correct tool for this job. So then people started coming up with their own representations. It led to graph databases, right? So there are multiple reasons for multiple ways to store the information. Knowledge graph is essentially a conceptual object. It's not a database storage technology, right?
If I summarize, uh, it is like ontologies and knowledge graphs are for knowledge representation and not for storage. So, what knowledge graph says that do not represent in the form of tabular structure, but do it in triplet form. But this is only representation concept.
Hmm. Yes.
And we do ER diagram, as we do
Uh, Dr. Jain, somehow the voice is not audible. It seems others are also facing the issue. Uh,
yes, sir. Please go ahead.
okay. You can still, you all can still see my screen, the presentation, right?
No,
No,
sir.
sir. No, sir.
Okay, just is it there? Is my screen there? Can see it?
Yes, sir. It
Okay,
is.
Yes,
Yes,
sir.
sir.
It is
Yes.
visible.
okay, okay, okay. So,
Hello,
yeah,
hello, Dr. Sumit.
yes.
If I might, this is PS Srinivas Kumar from IITM. If I just
Hi.
want to add one answer to the previous question
Mm-hmm,
that came up from Sarika,
mm-hmm, mm-hmm,
I think we can handle that by saying that relational databases by nature cannot offer inferences, whereas
mm-hmm.
yeah, it is the knowledge graphs that have the potential to offer inferences. Inferencing is one of the main uh, services that you can get from knowledge bases. So maybe you can just add that and proceed. Yeah, thank you.
Sure. Yeah, that's a good point. And that again ties into the fact that knowledge graphs are not just a way to store data, it's essentially a conceptual design where, as correctly pointed out, they can support inferencing. And just to give an example of what we mean by inferencing, so here, if you notice that we have these two facts, right? Rahul has mother Sonia and Priyanka has mother Sonia, right? So now, if our T box has also specified that uh, if the two entities share same mother, then they are also siblings, right? So if our T box has defined that, then the system could actually infer that, oh, so Rahul has mother Sonia and Priyanka has mother Sonia. So that means they are siblings because of the definition that is provided by the T box. So this is essentially called inferencing, right? And what it means is that a fact which is not explicitly mentioned in the data, the graph, can be inferred from the information that is present, right? You can derive this fact. So this is again one major motivation behind using knowledge graphs and representing data in such a way. In typical standard databases, you cannot do that, right? Knowledge graphs allow you to do that. And again, it's more like a conceptual structure. Like there are many inferencing engines that use databases, RDBMS as their backend storage engine, but all the operations that are done at the conceptual level, they are designed from the knowledge graphs point of view. So again, there are two issues, right? How to make use of that data, what's the conceptual organization, and then the underlying storage organization, right? And depending on your applications, storage might be relational database, a graph database, or a NoSQL engine, or some custom system. Okay, so let's move ahead. So here's a typical example of explaining or differentiating how knowledge or information looks like in, let's say, simple text or unstructured data as compared to when you have encoded in a form of a knowledge graph. So this is the Wikipedia page of Narendra Modi, right? So here you will find all the information about Narendra Modi that is of interest to you or is of interest to you. So his date of birth, his place of birth, where he did his schooling, which political party he belongs to. So all this information is present there, but it is present in natural language, which is unstructured, which could be ambiguous and very difficult for machines to interact. Now, this is, if you see, is the Wikidata page of Narendra Modi. So Wikidata is the knowledge graph counterpart of Wikipedia. So here you will see that all the information that was present, or most of the information that was present in text, is present in the form of a structured representation. For example, here you see educated at Gujarat University, educated at University of Delhi, residence New Delhi, residence 7 Lok Kalyan Park, right? So now this is a very structured and very clean representation for computers to use. So if there is a question, where does Narendra Modi live? System will just find this fact and give the answer that he lives in New Delhi at 7 Lok Kalyan Park. Now finding this information from text is very hard because the same information can be represented in multiple ways, right? Or it could be spread across multiple pages or multiple paragraphs in the same article, right? So that's the advantage that knowledge graphs offer. They are structuring your information, and hopefully you can make better use of them, right? Especially from a computer's point of view. So, what are some commonly used knowledge graphs? So all the major search engines, be it Google, Bing, Yahoo, or Yandex, they all have a knowledge graph which they are using internally. Then you have what is called as DBpedia. So DBpedia is a knowledge graph that is created out of info boxes of Wikipedia pages. And last I checked, has more than 800 million tables. That is around more than 80 crore facts extracted from Wikipedia. Similarly, you have Wikidata. Wikidata is very comprehensive community created knowledge graph from the same Wikimedia Foundation. And last I checked, it has more than 7 billion triples. I think this number is even outdated now. It is probably closer to 8 billion facts, 8 billion triples. That means 800 crore facts are present in Wikidata, which is huge. Imagine it is more than the population of human beings on this earth. So huge data. Then there is this system called Yago. It's an academic project developed and maintained at the Max Planck Institute in Germany. It also has around 200 to 50 million triples. And then in different applications in different industries, you'll have many custom domains with knowledge graphs built. For example, let's say some pharmaceutical company will have a knowledge graph for their medicine, diseases, their symptoms, those type of information. Out of all these, for your academic or for your research projects or just for fun, my recommendation would be to try Yago or DBpedia. Yago is a bit more, I would say, uh, comprehensive, has higher quality information compared to DBpedia, and it is in a reasonable size that you could process with, reasonable hardware requirements. Wikidata, though very comprehensive, it is it, 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 it is very it will require significant hardware infrastructure from your side, right? It has 7 billion tuples. So just to download the data, it will take significant bandwidth and significant time. And if I remember, I think when I downloaded it, it was close to 900 gigabytes or so in compressed format. Just to unzip it, it's a pain. It takes days. And after that, you need to have some very high configuration clusters to manage the data. Unless there is a specific reason for you to use such fancy data source, my recommendation would be to rely on either Yago or DBpedia. And all these three sources, they are free to, they are freely available. You can just go and download and play with them. But my recommendation would be to use Yago because of its reasonable size and high quality. If you are building say if you are a startup person, you are starting a company and you need comprehensive information and you have the resources, then you may want to go for Wikidata. But we want it will require huge computing efforts from your side. Okay. So with this background of what knowledge graphs are, what they encode, what they do, and from the look of it, it looks like they might be useful. So in IBM Watson, we decided the whole Watson knowledge graph effort with the aim so that IBM's clients, which is essentially the companies, the government organizations, we can offer them a way or we can enable them to organize the information that they have in a structured fashion and then make good uses or good applications on top of that. So that's the high level motivation or view you could see captured in this slide. You have different data sources out there, which we call as signals from different sources. These could be some information stored in their some databases, some tech reports, some product manuals, scientific papers, patent documents, intelligence reports. All these documents are there, right? These are disparate sources, right? What you do is you create a knowledge graph out of all these sources so that all the knowledge that is spread across these different sources is concentrated, consolidated in a single knowledge base. And once you have that, the way we developed the product at IBM was to first build the key high quality knowledge base and then a set of APIs, right? That APIs should provide some fundamental operations that can allow the end users to create useful applications built on top of knowledge graph. And these fundamental operations should be finding interesting entities from the graph, finding similar entities from the graph, traversing the graph, right? So what are the fundamental operations that we want to support and then offer them as APIs, and then the end users, the customers, companies, they can use these APIs to create their own apps. So for example, let's say a medical company, they can consider an app to answer medical questions. A sporting company could create an app to answer sporting relation questions. So I have some examples the slide here. You could have questions like what is tumor protein 53. This is a very simple retrieval based question. You get the question, get the answer. Who are the top players of Delhi Daredevils? So these are some basic simple questions. But then the more interesting applications would be what are the genes most similar to TP53 genes, right? So for example, imagine you are a medical researcher. Let's say today in times of COVID, right? people figured out that this COVID-19 virus is a type of coronavirus, right? So in drug discovery, what people did is, or what the medical companies are trying to do is, find out other viruses that have similar DNA properties to coronavirus, or the diseases that are similar in symptoms or effects to COVID, and then see what are the drugs that were helpful in those diseases. Can they be used for treating coronavirus, right? So that's your typical process of drug discovery. Now, in traditional way, what the pharmaceutical researchers do is they have to keep updated by the latest technologies and the latest research. And research is like 10,000 articles are getting published in. It is not easier, or it is not feasible for human beings to read and make sense of all these papers. But if you have a graph created out of these papers, you could do some traverses. Like, for example, let's say, oh, okay, coronavirus affects lungs. It has these symptoms. These are some other viruses that have similar DNA properties and they also affect lungs. But for diseases caused by those viruses, chemical X was useful. So can we use chemical X for treating coronavirus? Right. The system could offer these insights, and then the pharmaceutical researchers can do further evaluations. Okay, let me evaluate drug A, drug B, and drug C. All these type of applications can be developed. This is actually an actual collaboration we did with some medical college in Texas in automated hypothesis generation for drug discovery. Even a graph of these diseases, drugs, genes, molecules, chemicals, and other bodily symptoms, generate these hypotheses and present it to medical practitioners that for disease A, symptom B, drug X could be used. This is an hypothesis. So you generate high quality hypothesis, and then the medical practitioner can do further work and validate those hypotheses and whether it's a correct one or wrong. And in medical companies, this hypothesis generation is a very costly operation. So the typical time period required to create a new medicine, create a new drug, is on an average 10 years. And most of these 10 years, uh, the initial years, they are spent on generating these hypotheses, which are basically doing this research and establishing all these connections. So our idea was, can the computers do this hypothesis generation and reduce the time of drug discovery? So that was the high level idea of the project, and knowledge graphs were actually used there. If you are interested, you can actually go to my website and search for a paper in KDD 2014, 2015, uh, where we talked about some of these things. So again, it's an unsolved problem, but it's very interesting and is very useful and very applied, especially nowadays when drug discovery is the hot word because of virus. Okay, so as I described, in this whole vision, there are three steps that are required, or three questions that we need to answer. So first is identify the sources of data where information will be present. We need to answer this where the information will be present, and identify the data sources, and from those data sources extract and enrich and create a knowledge graph. Now, once you have created a graph, then the next question you want to answer is, what is it that out of this huge graph, what is the specific portion of the graph that the user might be interested in for their application? So you saw in previous examples that Wikidata has more than 7 billion triples, right? So if you create such a graph, so the first question you should ask now is, what is the specific portion, or what are the specific parts of this huge graph of that are of interest to my user? Where should they start? Okay. Once you answer that, then you start exploring the graph in that focused, or that specific region. And hopefully you work in that specific region and utilize the information from the complete graph. Hopefully, it will allow you to infer some non-obvious, novel information, some interesting insight, which was not obvious to you or not known to you, was not something expected or easy to derive, which is what we call as it will lead to a wow moment, right? So that's the goal. I mean, from a company's point of view, like company like IBM, if we say to some other clients that give us money and we'll build a knowledge graph and we'll do that, the first question will be why. So in order to prove the utility, you should be able to show them that if you do it this way, then it will help you find information which you were not expecting, which was new to you, right? Which was actually useful to you, which you were missing out by some other techniques. That was our selling point. And I'll actually, in the follow-up slides, I'll actually illustrate what I mean by that. Okay, and just a side effect, just a side point. In many of the applications, when we were building this, we realized that often we don't even know the correct answer. It's just that once you discover, then you figure out, okay, this was also possible. We were missing out on these things early, right? So, and that is what is make it more useful, right? Because if you know that, this is the answer I'm looking for, let's say, Steve Jobs. If you know this information exists, you will figure out some way or the other. But what's the unexpected information that you should look for that would surprise you, that would excite you, right? I'll explain it later with the help of examples. It will make more sense. Okay, so let's start with the first part of the question. How do we create the graph, right? And here I'll just give you an examples to provide uh, like a feel for what type of things that are required, what it means when we say creating a knowledge graph. And it's a very example-driven, practical kind of an slides, next 2 or 3 slides that will be there. I think the Maya's talk in the evening, she'll be delving deeper into a bit more hands-on approaches. So, but I hope it will give you a good idea and a feel of what is required in creating graphs. Okay, so let us say this is our sample input from which we want to create a graph. So this is nothing but first paragraph from Barack Obama's Wikipedia page. So if you see this paragraph, we have Barack Hussein Obama, born this date, is an American politician who served as the 44th President of the United States from this date to that date, blah, 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 blah. He was born in Hawaii. He grew up mostly in Hawaii, blah, blah, blah. So this typical information you find in Barack Obama's Wikipedia page. Now, note here that some of the words are underlined. These underlined words are the noun phrases or the entities that the system should find, right? And also note that there are certain terms uh, which are marked either a single star or a double star. Okay, so this double star is indicates that okay, so all the phrases which are marked with single star, they indicate that okay, let me explain it this way. Let's consider the first sentence. Barack Hussein Obama is an American politician, served as the 44th President of the United States. So in this sentence, there are 3 noun phrases that the system, let's say, could identify. Barack Hussein Obama 2, American politician, and who. So the star indicates that the system could figure out that in this sentence, all these 3 nouns, they correspond to the same entity. So Barack Hussein Obama 2, American politician, and who. They all corresponds to the same person in the real world, right? So that's what the star is indicating here. Now in the next sentence, the system figure out Obama. Obama was born in Honolulu. In the next sentence, he grew up mostly in Hawaii. So here he has this double star. So here the system is indicating that he in this sentence is actually the same entity identified as Obama in the previous sentence. Okay. So this is your typical problem of co-reference resolution, right? So let's see in the next slide, how does the graph look like? So on the top, we have Obama person, born at Honolulu, located at Hawaii. These are the facts that are extracted. And then on the bottom also, we have this subgraph called Barack Hussein Obama. He's the manager of United States. He's part of many Americans. La, 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 la. So the important point to note here is that the system identified Obama and Barack Hussein Obama as two different persons, two different nouns, right? Why is it that? Because obviously in the first sentence, it was just mentioned as Obama. The system figured out that Obama is a person. But in other sentences, he was mentioned as Barack Hussein Obama. Now the system doesn't know that Obama and Barack Hussein Obama are the same person. It just figures out, it's just smart enough to figure out that Barack Hussein Obama is a person, right? So the output graph essentially consists of two separate graphs. There are two nodes, Barack Hussein Obama and Obama, corresponding to the same real world person, same real world entity, right? So the first, so now this specific graph you can actually obtain from any modern name entity recognition system. Okay, so you could use tools like Stanford's OpenNLP. So I actually wanted to give a demo of Stanford's OpenNLP, but somehow just before the meeting I realized when I checked that their website was down. So I'm not able to show the demo, but after the talk you can actually go to Stanford OpenNLP web page and they have a demo site. On the demo site you could enter a piece of text and then run the toolkit on it. They have a run button and it will create identify entities and their relationships. So you can use that to create your own graph. So I wanted to give a demo, but I'm sorry, the website is down, but you can use it. And there are many other toolkits also. So there is this OpenIE toolkit, I think, which is developed at IIT Delhi, and other OpenIE systems, open information extraction. They can do a lot of this work for you. So all this, which is shown on this slide, you can do by using OpenIE systems. Okay, so for the OpenIE systems, they will give you information like this. They identify that in a given piece of text, this is the named entity, and these are its relationships. But often what you will find is that many in natural language, the same person could have multiple names. The OpenIE systems will treat them as two different persons. Okay, so now this is problematic. We somehow need to figure out that, Obama and Barack Hussein Obama, these are same person, so they should be clubbed together. And why should we want that? See, one information is that a lot of important information about the same entity will be split across multiple nodes in the graph. So if I say, is Obama a president of the United States, then the entity called Obama doesn't have that information, right? But entity called Barack Hussein Obama has that information, manager of the United States, right? So, but if you could somehow merge these things together, then you will have a more complete information about the entity called Barack Obama. So this is your entity resolution problem that is typically handled in NLP and machine learning. This is what entity resolution is doing. So let's say we do that, then you notice that now Barack Obama, we now have an entity called Barack Obama in our graph, and it contains of all the relationships that were captured by the two different entities that were there, right? So in the entity resolution step, what we have done is, let's say by using some external knowledge, some human intervention, or use of some dictionary that told you that, Barack Obama is the name of a person called Obama is the name of a person, and that person is also known as Obama and Barack Hussein Obama. So let's say you had a dictionary like this, or you had some human intervention that could tell you that, node 1 and node 17 are same, merge them together. So once you do that, now you will notice that this graph is much more cleaner and is much more compact compared to the graph that we see here. Okay, so now there is one more problem you will see. So notice here that Hillary Clinton is a separate subgraph here. Hillary Clinton affected by primary campaign. Now, what has happened here is that if we go to the original sentence, the system, the named entity recognition system, it was smart enough to figure out that Hillary Clinton is an entity of type person, but somehow it was not clear to the system, or the system did not have enough confidence in this predicting, like what is the exact relationship between Barack Obama and Hillary Clinton. And actually, if you see, in many cases, it may not always be possible to find a single well-defined relationship between two entities. Right? It is not able to, like, you may not be able to define how Barack Obama and Hillary Clinton are related together. Or maybe your T box did not have that information, or the system was not able to identify, or it was not trained to identify those types of relationships. So you can only train your systems on a finite set of relationships, right? So let's say you trained your system to identify 50 or 100 types of relationships. But as I said, the knowledge in the real world is almost infinite. So you never know in the new documents, there could be some other type of relationships and the system is not able to recognize them. So what we did is we added a heuristic that whenever the system is not able to identify a clear relationship between two entities and the entities are in close proximity to each other, let's say they are in the same paragraph or they are within 3 or 4 sentence windows, then we say that, okay, we don't know what is the relationship between these two entities. It's just that these entities have appeared together in the text. So we add a dummy relationship called collocation. So here, if you see, we have added this connected Hillary Clinton to Barack Obama with a dummy relationship called collocation. What collocation is telling you is that we don't know the exact relationship between Hillary Clinton and Barack Obama. It's just that they are co-located to each other in the input source. They are close to each other. That's all we know. So essentially, it is saying we know there is some relation, but we just don't know the name of the relationship. We don't have enough knowledge. And the advantage of doing that is that your graph again becomes a bit more consolidated. Otherwise, you'll have a lot of these small subgraphs, and your graph will have many independent connected components, right? So you are losing out on a lot of information because of this disconnect. So just to overcome that, we had this heuristic and connected this graph to improve the connectivity, right? Uh, and how does it affect actually? Let's say, so we take we took Wikipedia as our input source and CIA fact book as our input source. We had two corpuses, right? Wikipedia and CIA fact, so information from these two sources. So what we did is when we ran the first step, like just apply the open information extraction system and name entity relation systems out of more than 5 billion documents, we got 176 entities and 145 million relationships. After that, there was this step of entity resolution, right? We brought together many entities, merged together many entities. So notice here that the number of entities reduced from 176 million to 23 million, right? It's a drastic reduction. And what is happening is that there are many persons, let's say Steve Jobs. So in some documents, Steve Jobs is mentioned as Steve Jobs. In some documents, he is mentioned as Steve Jobs Jr. In some documents, he is mentioned just as Mr. Jobs, right? So there are all these different entities in the graph corresponding to the same person. So you combine them together in a single person. So obviously the number of entities will reduce. As the number of entities reduce, what it means is number of nodes in the graph reduce. Number of nodes in the graph reduce, that means it will be easier and more efficient to process the graph, right? So that's an advantage. And you also consolidate all the information together. Also note that number of relationships have also reduced, right? And why this has happened? Because let's say there was a document A where it was mentioned Steve Jobs is CEO of Apple, This is one relationship and one fact. And in some other document, this was mentioned, Mr. Jobs is the CEO of Apple. So there is this second relationship or second fact. But once you have clubbed Steve Jobs and Jobs, then both these facts become a single fact, right? So that's why the number of relationships also reduced. So what has happened is you have consolidated the information, you have made your graph more clean, and at the same time, you have reduced the size of the graph. So it will be much more easier and efficient to process. From 176 million nodes, you have come down to 23 million nodes. Almost a 1:8 comparison. Now, in the final step, we did the expansion of this co-location thing I talked about. There are many relationships where we don't know the exact name of the relationship. We saw them very close together in the input module. Say that there is a co-location relationship. So after doing that, the number of relationships again increases. Note that the number of entities will not be changed, right? Because we have only added new edges in the graph. So now you will notice that adding these co-location relationships, what it is doing is it is essentially increasing your recall at the uh, loss of precision, because you are adding some relationships. So essentially you are saying, okay, I know there is some relationship between Barack Obama and Hillary Clinton. It's just that I don't know the name. And also for my application, I do not want to lose out on this information. Hence, I'm retaining it. So essentially, in a sense, I'm increasing the recall, right? But let's say if there was some application where you only wanted information which is highly precise, which is highly confident. So this application require that only tell me some information only if you are 100% or 80% or 90% sure, right? If you're not able to figure out the relationship, leave it. It is not important to know. That's a high precision application scenario. In that case, you should have, or you could have avoided this expansion step, right? Because it is essentially a way to make sure that you do not lose out on some information about which you are not very sure. If you don't need that, you can just leave that. So these two are just two extremes, right? High precision and high recall. So it's just a practical trade-off. So the same approach we actually deployed and used for multiple customers of IBM, and would actually use it. So the largest customer was government's uh, the federal client, and there they had like huge amount of data, almost 100 million intelligence reports, news articles, and other internal reports, and we could create a graph of up to 100 million entities and up to 5 billion relationships, which is quite a big graph for a single specific. So before we, so that's basically I wanted to cover about construction of graphs, some practical aspects. I wanted to go over, as I said, hands-on demo, but somehow the Stanford's core NLP site is down, so we will not be able to do that. So what we'll do is we'll now dive into applications. But before we do that, any questions till now? Any questions? Any comments? I'll go to the chat box. I'll stop the screen and I'll go to the chat box.
Hello, Sumit sir.
Yes.
Can you share the link that you have told earlier about Stanford NLP portal on chat box?
Yeah.
We can call.
Yeah, sure. Let me just do that.
Thank you, sir.
I pasted that is corenlp.run. I'm not sure if it is up now, but it was not there when I was trying. So, okay. Any other questions?
Yes,
Sumit,
excuse me, Dr. Bhatia. I have a
Yes.
question that sorry, is there any tool to extract the entities directly? Like if I have a sentence, Barack Obama was the president of USA. So there are two entities and one relationship, and I want to show as a graph connected as I give the sentence, and it should be converted into a graph. So is there any online free available tools to like you have shown a paragraph and you have highlighted the entities, but this work can be done by any tool? Is there any applications?
Yes, so I just shared the link in the chat box. So the tool I wanted to give a demo of Core NLP, Stanford's Core NLP, and you can also search for Open IE system, Open Information Extraction Systems. I think
And
IIT Delhi has a tool which is really available. So you can try all these tools. And if you go to IIT Delhi's website, Professor Mausam, MAUSAM, Professor Mausam, he
okay,
is leading a team that is working that is doing a very good work on open information extraction. So they do have a lot of open source toolkits available at their project pages. So you could search for Professor Mosam, IT Delhi.
okay,
Uh, you could search for open information extraction systems. And one tool that is available is Stanford's Open NLP or Stanford's Core NLP. Search these things, you will find a lot of open source tools, a lot of code examples to do the things which I just talked about. And Core NLP has an online demo,
okay,
so you can just use the online demo to just get a feel for it. But if you want to do it in your product, your projects, you'll have to download their code library, their trained models, and they have a lot of coding examples. I think in Java and Python also, so which you could look into. So that should help you get started and doing something similar to what I have described.
and there is there any other query language to entrancing with the knowledge graph rather than other than Sparkle? Like I have I didn't work, but I have I got about the cipher queries, but how they work with this?
Uh, Sparkle is the preferred language, right? Because it makes use of a lot of constructs in that are useful in knowledge graphs. Again, SQL is something which was not designed for this thing, right? So if you want to do these things, I would recommend brushing up your concepts in Sparkle and other related technologies, or you could do it write code to do what you are looking for, right? But I would say if you want to do something related to inferencing and knowledge graphs, you should start looking into Sparkle. I mean, in theory, you could do it by SQL also, but it is not an optimal way of doing that, right? So it's
Okay,
just the right tool for the right problem, right? You don't need a Ferrari to go and get sabzi from your local market. For that,
okay,
a rickshaw will also do. But then you
okay,
don't need a rickshaw if you want to go on a highway, right? Then you need a better car. So use the better tool for the problem and not just, uh, try to do everything by the tool that you are comfortable with. Find out what is the optimal solution for what you're looking for and then use that. Otherwise, you will not be able to make best use of the capabilities that system, the concepts, and the tools offer.
all right. Thank you, Dr. Bhatt.
Sure.
Sumit sir,
Yes.
I want to know how we can compute the accuracy of this enrichment.
So accuracy will be computed by like typically what you do is you take a small sample of documents, do a manual annotation, and then compare the output of the system with that. Obviously, you cannot do it for the huge, all the millions of documents. So you take a sample, good quality small sample, do the manual annotations, and then compare the output of what the system is producing to what the humans have evaluated, right? I mean, that's the best way of doing the evaluation.
Are there any other questions for the participants?
Sir, I can see some questions in this chat. Let me read it out for you.
Sure. Sure.
One of them is, are all the standard knowledge graphs prefer graph DB to store their triples?
So, in most cases, I would say yes, they are the optimal ways of storing it. And then even in graph databases, there are multiple technologies. You have something like GNS Graph, you have Neo4j, or you have systems like Stardog that are optimized for storing RDF data and support Sparkle engines, right? So again, your choice of storage technology will depend on what you want to do, right? It's not a one size fits all answer. You have to figure out what is it that you want to do. Then compare the features offered by different systems. Then select the system which meets most of your requirements, right? It's not a one technology that will serve all your requirements and purposes.
Sir, what about triple stores like Gina TDD?
Yeah, triple stores are good, but Jenna may not be able to scale well in my experience. Stardog might be a better option. Again, I think if it's an in-memory database or if it's an on-base database, all those issues will come into picture. But Jenna is a good start for small-scale applications.
Okay. Abhishek, any other queries? Please look into the chat.
And one more is there. May I know the difference between XML schema and an ontology? So,
And a more general concept, right? XML schema is just for XML data. It cannot encode all the complexities that you have in typical ontologies. Right. So if you have attended, I'm not sure if the session by Professor Raghav Muttaraju has been held, or if it will be a later session. I guess he will be covering a lot on ontologies, right? What are the different properties, different things that you can encode in ontologies and using them, right? So, I mean, there are a lot of things that you can do in ontologies, but not in XML. How do you define relationships? How do you define properties of it? They're not in very different. It's uh, just more like a markup to tell you that in my data set, this concept maps to, let's say, a header, this is these types. Technology is much more rich. To attend Professor Raghav's lecture if you haven't, if you were not planning to do so.
Yes, sir. How long is the first session there now? Because after this, we can take a 5-minute break before starting the next one.
Sure. So I think it was from 10 to 11:30, right?
Yeah.
We have, I think, 11:20 now. So
It is 10
there are
minutes.
no more questions.
Hello,
Yeah, it is 11:20.
Dr. Bhatia?
Yes.
Yeah, I think I can take that question on XML schema versus ontologies if you allow me.
Sure. Please. Sure, please. Go ahead.
Yeah. So I would like to say that, in XML schemas, you can represent semi-structured data, and it's again more like a data, representation mechanism. It's again like something like a schema. So like object schema, relational schema, it's just a schema. It's one way of schema. Whereas in an ontology, because of the standardization of the ontology frameworks, the meanings of the various terms that we use kind of gets fixed, and so it's possible for us to convey knowledge in ontologies, which is not possible for us to convey in XML schemas. So that is the main difference between XML schemas and ontologies. I hope I have answered the question. I can further expand if you are still having some doubts about that. Again, this is Srinivas Kumar from IIT Madras.
Thank you, Srinivasa. So, Dr. Sumit, how to go forward?
Sure. So I think if there are no more questions, we can discontinue the session and meet for the next session. I think that was scheduled at 11:45. So we can start at 11:45 with that, right? That works.
So we'll come on the same meet link as the speaker is the same. So we'll come on the same meet link at 11:45 back to listen to Dr. Sumit again.
Okay. So should I use this meeting link, or there was a different link for afternoon session?
Yeah, actually we announced with the same speaker. We announced that we will use the same one. So let us now
Okay.
use the same link.
Okay, sure. So we'll use the same link. Okay.
Morning.
Sure. Sounds good.
Yeah, for all the participants, again, it is the same link as it is going right now. That is the morning link will continue. I will put the same on the WhatsApp also. Yeah, thank you, sir. Thank you. We'll meet at 11:45 back.
Sure. Thank you.